Alright, today's video we're going to take a look at more of a review from Algebra 2 than anything that's basically related to calculus. We want to make sure that we understand summations and summation notation for an application use in our integrals and in our Chapter 5 where we're introducing the idea of area under a curve. So what we're going to be working on today is reviewing both what is a summation and the symbols for summation, and kind of working with both a closed form formula for the summations, expanding them, and so on. And hopefully you will remember some of this from your algebra classes in previous years. So basically what we're going to be looking at is this idea that we start to look at a sequence of numbers. And usually our notation for this sequence of numbers, the variable a represents a number in the sequence, but because we have several numbers in the sequence, we give them basically an index. And this index is going to kind of give you an idea of your position in the sequence. So typically your n is less than m because you're going from like maybe the 5th term in the sequence to the 10th term in the sequence. And so this just is a notation that allows us to look at a sequence A and look at each of the terms in the sequence A. And that typically after we've taken a look at a sequence, then what we're going to want to do is we're going to want to sum up all the terms in the sequence, and that's called a series. And when you were in Algebra 2, you basically looked at two very special types of sequences and series, which were arithmetic, where to get from one term to the next term you would add a common difference, called a common difference because to find what you add you would take the difference of two consecutive terms. Or it would be a geometric sequence where you have a common ratio where you multiply by a common ratio to get from one term to the next term. Again, ratio because to find it you would take the ratio of two consecutive terms. Alright, so right now what we're going to look at is this idea of the series where we are adding up all the numbers in our sequence. And this form right here, this idea where it's written all out, is called the expanded form. But a lot of times mathematicians, we like to write things very concisely. So what we want to do is we want to be able to use a notation that means the same thing as the expanded form, but that allows us to kind of do a shortcut for it, or shorthand notation. So when we take a look at this, we're using the capital Greek letter sigma. So whenever you see this sigma notation, that means that we are doing a sum. The index variable, a lot of times, and especially what we're doing, we're going to be using I, but it can be any variable you want. So you identify an index variable, which is going to identify which terms you want to add together. You're going to have a starting value, which is going to be here. Which term do you want to start with? So your starting index or your starting value. And then up at the top is going to be where you want to end, or your ending value. And then this a sub I, right now we kind of just have a sub I right here, which is saying we're just going to sum the terms of this sequence together. And you would plug in n and then the next one and then the next one and so on up until you get to m. But usually in that location, a sub I, you will have some kind of a formula where that formula is a function of I, where you find each term in the sequence by using some formula where you plug in 2, 3, 4, 5, 6, each of your index values, and allows you to find them. And so the I is your index of summation, okay? And we're going to add up all the terms in the sequence for all the integers. These starting value to ending value, you're only, because it's position in the list, and your position in the list is going to basically be an integer. Now you actually can do it with negative numbers and positive numbers, but in the context of what we're going to use it for, we're pretty much going to always start at 1 and go all the way to a positive value. Like for example, if you're taking a look at these two examples right here, you have your sigma notation, and it says we're going to sum the number of terms from I equal to 0 to 4. Now let's talk about number of terms. If I want to know how many terms I'm going to actually be adding up, I take the end minus the start, but then you always have to add 1 to that, because 4 minus 0 is going to give you 4, which is the number of terms between 0 to 4, and then you got to add your starting value back in. Just think about it. Think about how many actual numbers you're looking at from 0 to 4. So we know that we're going to have our 5 terms, 1, 2, 3, 4, 5, and that our job is when you see this formula right here, here is our formula for each term, a sub I, as a function of I. And so to find each term, you're going to first plug in 0 into the I position. You're going to plug in 1, you're going to plug in 2, you're going to plug in 3, you're going to plug in 4, and then you would simply calculate the sum. So the idea is you should be able to become very handy at, if I give you the sigma notation, you should be able to give me the expanded form. The calculation of the actual answer is more just arithmetic and not really something I'm worried about. You would just do that on a calculator. The second part of this, though, is that you would have to be able to work backwards. If I give you the expanded form, you would then have to be able to recognize how to figure out a formula for each of the terms and then be able to write it in your summation notation. Now, typically when you're working backwards, you first look in each term for where you see a counting number, where things are starting at a beginning value and counting up. And you'll notice that in both of these locations you can kind of see that you have your 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. That helps you identify where your variable is going to be in your formula. And notice that you have your I and I here that is in the same location as these counting numbers. Now, sometimes it's not quite as simple as the easier ones like this one. In this one, if you take a look at our summation notation here, we're going to go from 4 to 6. So that means we're going to have 6 minus 4 plus 1, or 3 terms. We know that we're going to plug in 4 first. So we have 4, and then 2 times 4 plus 1, 9. And then we plug in 5, and then we plug in 6, and then we stop. And so we have our 3 terms that we're adding together. So typically going from sigma to expanded form is fairly straightforward. Now what we want to do is, let's look at this one for the working backwards part. You still look for where you have counting, and I would look here and say I do have counting where it goes 4, 5, and 6. You look for things that are changing. Notice I'm not even looking at the 2 because the 2 is constant through each term. But I also see that I do have a change here as well. I have a 9, an 11, and a 13. So I kind of have to take a look at this and decide when I am trying to work backwards, what do I want to do? Now because this goes 4, 5, 6, that's going to kind of give you a start to an end. But then you have to figure out, how is 9 related to 4? How is 11 related to 5? How is 13 related to 6? And so it becomes kind of an algebra problem where you're trying to come up with a rule for how to determine a formula for the second exponent by plugging in, say, 4, how are you going to get the 9? And now first thing you notice is that they're odd, and we know that we can typically do odd numbers by twice numbered plus 1, and then you can look at it and be like, oh, okay, 9 is 2 times 4 plus 1, and this is 2 times 5 plus 1, 2 times 6 plus. So you kind of have to reveal sometimes the formula that you're looking for your function of I. Now notice kind of when we're looking at this that the 2 and the x, these are the things that are in common to every term. So they're not the part that's changing, so they don't really have anything to do with the I part of it. They have to do with the kind of just structure of how you're getting each term. And notice that when we're doing this, you don't have to end up with a number like we did in the first one. It could be something where it's creating like a polynomial here. Now typically kind of more what we're going to see in the calculus section here is this idea that we're going to have two things going on. Now, in this notation, I'm using x sub I star, but I think what I'm going to do is I'm going to kind of change this x sub I star and change it to talking about using c sub I. Because in calculus, what we're used to doing is we're used to choosing, say, let x equal some value c in an interval. Okay, so a lot of our problems, we're trying to find the derivative at x equal to c. We're trying to estimate how fast we're going at x equal to c. So c is our kind of notation we've been using in calculus to identify a value that we are choosing. And what we're going to do is we're going to change that to kind of talk about the value c sub I. So we're going to choose x values from a certain interval, and those x values, I'm going to kind of rename this as c sub I. I think I like that notation better than what we have in this set of notes. And so that when we look at it that way, we're going to have basically the sum of a function of these c sub i's that I'm going to choose. Now, we might have, notice because it's not f of I like I was doing up here, but it's f of c sub I, that if I'm going to do that, typically what that basically means is you're going to have a formula embedded inside of another formula. So c sub I might be something like a plus delta xi. I'm kind of previewing something that's going to come. So you'll have a formula for calculating each c value you want to pick, and then you would have a function that you are plugging those c values into, and then that will kind of give us an idea of what we're going to be working with calculus. And once we have this kind of idea down, knowing how to expand it would be you calculate each c sub I, and it's going to be a function of I, and then you plug that into your function, and then you would basically calculate each of your terms. So you would basically have four inputs, 4 minus 1, which would be 3 plus 1, 4 terms. So you would be calculating your c sub 1 first, and then you would plug that into your given function to find an output, and then you would add that to f of c sub 2, and then continue until you get all of your terms. Okay? And so the idea is being able to work from one back to the other and so on. Now, of course, this idea of using these summations, we kind of need to know the properties. Now, the first thing I want to say, kind of going into this property, that you want to be very careful, because this is where we start to get a little confused in calculus. And where we can get confused is that you have properties for limits. Okay? And maybe let's review a little bit of what we had for the properties for limits. Let's see if I can just fit it in right here. If I had, well, I won't write it down, we'll just do it in words. If I was going to take the limit of a constant times a function, you go, well, what do I do with the constant? I can pull the constant out and then take the limit of the function. All right? We had a rule for derivative properties. Derivative properties are if I have the derivative of a constant times a function, then that would be the same as the constant times the derivative of the function. So we kind of like this rule because the property for summation works exactly the same way. If I want to sum for some index variable I, and this is the key, you're going to have all sorts of letters in the problem. You first have to recognize that your index variable is your I. So anything that is not the I is going to be a constant. So this c is a constant, has nothing to do with the I. This is not c sub I like I was using up here. So this constant c, that if I'm going to sum a constant times the terms, then I can pull the constant out. Now let's think about why that is. That if I were to expand this, I'll just kind of fit it in right here, you would take your c sub a from your, this is I sub 0 for starting value, make it a little I sub 0, and then you would do c a, the next one, I sub 1, plus c a I sub 2, and you would consider all of these up until you get to a I sub n. And notice that properties of algebra from algebra 1, that you now have a constant in each term that you are summing. So what I can do is I can factor it out and have the terms a and a sub I 0 plus a sub I 1 plus all the way a sub I n. And so now I have c times a sum, and that's what we're basically saying here. So we can factor constants out of a summation, just like you can factor them out of a limit, just like we can factor them out of a derivative. Now, the next thing has to do with the property of if I actually had two things in here that I'm adding or subtracting. Now, let's think about this. The limit of a sum is the sum of the limits, provided the limits existed. The derivative of a sum is the sum of the derivatives, provided the derivatives exist. And then you have your summation of a sum is the sum of the summations, that we can break up a summation across sum or difference. And again, it's playing on your algebra rules from Algebra 1, that if I were, basically associative and commutative, if I were to sum these over this interval, and let's just assume this is just, I'm tired of writing the I sub thing, let's go 1 to 5. So if I were to do this, I would have A1 plus B1 plus A2 plus B2 plus, and then we would keep going until we got to our n, AN plus BN. Okay? But because this is all addition, even within these parentheses, we can regroup and reassociate as we want. So I can rewrite these and put all the A's first, and then put all the B's. And then notice that I have the sum of the A's plus the sum of the B's, and that's basically what we're saying. And it works for subtraction too. And now kind of the other thing is that when you're doing this, make sure you not only know the properties that we can use, know the properties that you can't use. So while I can distribute kind of this idea, I can pull constants out and I can distribute the summation over addition, notice that you cannot distribute summations over products, that this is not going to be true. I cannot distribute the summation over division, and that this is not going to be true. So be very careful and make sure you pay attention to these kind of arithmetic rules that we're going to be using for summations. Now, the second thing here is this idea that I don't always want to have to take my summation, when you have it in your sigma form, turn it into an expanded form to then get the final answer. That can be very tedious. I mean, what if your summation has 100 terms in it? I don't want to have to write out 100 terms and then type them into a calculator to get a final answer. So one of the things that we do with summations is we basically create shortcut formulas. We're going to create a shortcut formula to skip over the expanded form, and that will just simply give me the final answer. We call that a closed formula or closed form of the sum. That it is a formula based only on n, the number of terms that you're basically going to be using, and it will help me get my sum without having to write them all out. And a lot of them make sense, and I'm not going to prove these. In your algebra classes, hopefully you took a more in-depth look at this, but for what we're doing in calculus, you pretty much just need to memorize this set of formulas. Now, the first one should make kind of common sense. If I am going to sum a constant n times, okay, because n minus 1 plus 1 would be n times. How many times did I add the constant? N times the constant times n. That should make sense to us. I'm not going to prove these, but every time that you sum the from 1 to n of just I, which is basically an expanded form, 1 plus 2 plus 3 plus dot 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 plus n, that when you sum up the integers, this would be a formula for you. If I am going to sum the squared integers, basically you're doing 1 plus 4 plus 9 plus 16 plus 25 plus n squared, right? And that if I want to sum the cubes, the triangular numbers, 1 plus 8 plus 27 plus up to n cubed. That instead of doing this expanded form, okay, and then this is just showing you that you're doing c plus c plus c plus c. So instead of putting this in an expanded form and then typing them into a calculator, that I can use this shortcut formula to calculate them. Now, what this actually does for us, another way of looking at this, even if I'm not calculating an actual sum final answer value, that whenever I see a sigma in a problem, that makes the problem complicated. So what I can do is I can take it out and I can replace it with a formula that no longer has the sigma notation in it. And that's what we're going to be using it for in the applications in Chapter 5. All right, and then here's an idea about how to use these properties to evaluate sums that may not be easy to do by hand. For example, I really do not want to expand this out because I would have to plug in 1 and then square it, so give me 1, and then I would have to plug in 2, which would give me 1, and then I would have to plug in 3, which would give me 3 minus 6, negative 3 squared, 9, and you would have to do this all the way until you got to 100, and plugging in 100, 3 minus 200, and get whatever 197 squared is. Now I obviously don't want to spend the time to write all that out and do that the long way. What we can do is we can use these properties to evaluate it without expanding it. So the first thing we're going to look at is that, remember, there's no squaring is like multiplication. You can't distribute over multiplication, but what we can do is FOIL out and turn this into a sum. And then once I turn this into a sum, notice that I am now going to basically distribute the summation through the subtraction and the plus, so that gets me to here. Then I'm going to leave the 9, but see how I'm going to pull the constant in front to here. And so that kind of sets me up for a way to get rid of the sigmas using the shortcut formulas. So using the formulas above, from here, remember you're going to do your constant times n, that's that formula. Then you have your minus 12, and then this is your formula n plus 1 over 2, where n is 100. And then here's my formula n plus 1, 2n plus 1, all over 6. And so I'm basically taking out the summations and replacing them with their shortcut closed formulas that then allow me to directly calculate it in a lot less steps than figuring out 100 terms and then adding them together. Okay? And so that's kind of where we're going to use this. Now let's do some examples. And again, I'm only really doing this section because I want to prepare us for what we're going to be seeing in the section 5.2. So we're going to do some examples, and then you'll have some homework that will deal with each of these examples. And you'll need your own paper for this section. I don't have this typed up. We're just going to kind of work our way through some of these. All right, and again, we're just practicing skills right now, just making sure you understand summations. So the first thing I would like you to do is I'm going to want you to be able to find an expanded form and calculate the sum. And then I'm also going to show you some shortcuts on the calculator for calculating these, although you're never really going to need to use these calculator commands for these sums in the AP, but just to kind of help you check as you're going. So for example, if I were to give you the sum I equals 1 to 4, and then we're going to start jumping right in with some nice complicated formulas, plus my I plus 1 cubed. So your job is to take this and I want you to expand it. So first off, how many terms are we going to have? 4 minus 1, 3, plus 1 gives me 4. So there will be 4 terms that we're going to be adding together here in order to calculate my sum. And then you basically go, hey, I plug in my 1 and I calculate what I get. And that's nothing more than arithmetic. I'll leave you to verify that if you plug in 1, you should get 8. If I plug in 2, I should get 28. If I plug in 3, I should get 68. And if I plug in 134, or if I plug in 4, I should get 134. Okay? Okay, and so you can verify that. And then after you get this, you simply go, hey, add these up, and you get 238. Now, to do this on your calculator, all right, there's a couple of different ways that you can do sums on your calculator. Now, some of you have some nice features in the newer calculators, have summation notation on them. So if we take a look in the math menu, we'll notice that one of your choices is the summation notation. So I can choose this. Now you can put I as your variable. That I have to do alpha, and I don't. So I can choose to name the variable anything I want. I'm going to call it x for convenience. It goes 1 to 4, so I fill in my lower limit and my upper limit. And then I'm going to put in a formula, just like they did, for calculating it. So we had our x minus 1 squared. And then we do our x plus 1 cubed. And then we just basically let the calculator do its magic and we check that we got the right answer. Now another way to do this is to go to your stats. For those of you that may not have that sum, I can edit the list. Let me come up here just in case you didn't know. You can clear out your list by simply highlighting L1 and hitting clear. You can highlight your L2 and hit clear because I'm going to need both of my lists. And so what I'm basically going to do is I'm going to think, well, what do I need? I need to go 1 to 4. Now you actually can do this using a command down here in your catalog. I'm going to go to my catalog just to show you something. We type in S because I want to go to the S in the alphabet, and I'm going to go down until I get to sequence. And so I'm going to choose that command. And so I'm saying L1 is going to be a sequence because I'm going 1 to 4. And I'm basically going, hey, this is going to be my variable x. And I want x to run 1 to 4. And let's see if I've remembered my notation correctly. And of course I did not. So let me go to and let me think about, oh, formula. I know what it is. That's my formula. Then you put your variable, then you put your start value, and then you put your end value. Let's see if that's it. It's either that or I have to put a delta x in here somewhere. Let's see what happens. There we go. All right, so I can put my sequence in. I want to go the first to the fourth. And then what I'm going to do is I'm going to come over here to L2, and I'm going to put in the formula for getting each term, which would be what you had in your summation. So I'm going to have, but now you got to remember your L1 is your variable now. So I'm going to do my L1 minus 1 squared plus my L1 plus 1 cubed, and then hit enter, and then it fills in, see those values that we came at before. And then I want to sum those up, so I can quit out of this. And I can also go to the catalog. I'm going to go to T because sum is at the end of the S's. So that way I can go to the T's first and then just work backwards. There's a sum command on the old calculators too that I can choose that. And I can basically sum L2 and it will tell me the sum of the list as well. Okay, so a couple of different options that we're looking at on the calculator. All right, let's look at another example. Now, this one, I gave you the formula, you expanded it, and found an answer. So that's all pretty basic. Now, in example 2, what I want to do is I want to work the other way. I want to find the summation notation from the expanded form. So in other words, you're going to work backwards. So now typically in this case, I'll give you something. I'm going to do several of these because these warrant a little bit more practice. So if I were to come in and give you 1, 3 times 1 plus 1, 3 times 2, we'll start with the easy one, 1, 3 times 3 plus 1, 3 times 9. And I want to rewrite this into this sigma form. So we're going to write our sigma, and now we start looking at it. and we go, do we see something that is counting? What's the changing part of this? The 1 is the same all the way. This 3 is the same all the way. Here's where the change is coming in. 1, 2, 3, up to 9. Now this is an easy one, starting easy. You realize, oh, I started at 1 and I went up to 9 and I went increased by 1. So I must be having I equal 1 to 9. And then you put in what stays the same, 1 over 3, and then whatever was changing becomes your variable. And so we've written it in its sigma form from the expanded form. All right, let's take a look at a second one. All right, now in the second one, let's say it looks like this. 1 minus 1/4 squared plus 1 minus 2/4 squared plus dot 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 1 minus 4 over 4 squared. All right, so I want to write that in sigma notation. So again, we put our sigma in and we start looking for what is changing. The 1 stays the same. The denominator 4 is staying the same. The square is staying the same. What's changing is right here. All right, so I kind of look at that and say, again, starting with the obvious ones, I'm starting my variable at 1. I'm going to 4. And then I simply put in everything that is the same. And then all I have to do is put in my variable. My variable is I. All right, let's look at one that might be a little bit more difficult. Let's look at C. And this one, I'm kind of working toward what you're going to see in calculus. This is more of what we would see in the calculus context. I might have something that looks like this. And actually, I'm only going to give you 2 terms, the first and the last. All right, so we want to write this in the sigma notation. And again, the key here is to recognize what is changing. So when we take a look at this, the 2 is the same in both, the 1 is the same in both, the n in the bottom is the same in both, but what you're seeing is this one had a 3 and that one has a 3n. So, and then you go, wait a minute, it doesn't go like 3, 4, 5, it's going 3 times 1, then it must be 3 times 2, then it must be 3 times 3, up to 3 times n. So that's where our variable is going to come in. But as complicated as the rest of it is, it's pretty much all the same. So I would say my I goes from multiplying by 1 up to multiplying by n, and that my formula is going to be 1 plus 3i over n squared times that 3 over n. And try to resist. Remember, your variable in the summation is the I. The n itself is going to be a number that you're just going to plug in and you're going to know. So it's the I that is your variable that's changing through the summation. All right, now for our third example is this idea of now that we can go from sigma form to expanded form to sigma form, really the objective we have is to basically use the closed formula to evaluate without expanding. So let's go to example 3 here. So we want to be able to evaluate the sum without expanding using the closed formulas that you have in your notes. You might want to have your handout handy while we're doing this. So for the first one, and again I'm going to do a couple of these because this is starting to be where we're going to be using this. So I have the sum I equals 1 to 10 of I squared minus 1. Now I certainly could expand it and evaluate the sum that way. It's only 10 terms. However, we're practicing not having to expand it. So what we're going to do is we're going to realize that we can distribute a sum over subtraction. So we would first rewrite this as I equals 1 to 10 of I squared minus the sum I equals 1 to 10 of 1. Now recognize that just like in prior sections, language and math communication is important. You're not allowed to just stop writing things. You have to put all the parts. If you're going to do your sigmas, you have to have a lower limit and an upper limit with your index and your formula. So don't get all lazy when you're writing these out. Actually write them nice and neatly. Right? And then once I get to here, I recognize I have the sum of I squared, which is going to be a formula. And my n in this problem is 10. Okay? So n equals 10. That's what we want to keep in mind when we're doing the closed formula. So for me to calculate the sum of I squared, remember that just kind of reminding you, the sum I equals 1 to n of I squared was going to be your n plus 1 to n plus 1 all over 6. So that's what I'm basically using to do this. So I keep this stuff in mind. And I go, oh, I want to evaluate this, so I'm simply going to go 10 plus 1, 11, times 2 times 10 plus 1, 21, all over 6. That's going to take care of the first part. And that this is the sum of a constant, which is nothing more than the constant times n, which is 10. So I go from here straight to here, and then you can simply calculate your sum, and it is going to be 375. And you can verify that by using your calculator. All right, let's take a look at another one. So I have the sum I equals 1 to 15, and we're going to do I minus 1 squared. Now, here the problem is you have to remember that sigmas do not distribute over multiplication. So if I want to basically evaluate this without expanding it, what I'm going to have to do is turn it into a sum in here, which means we have to do some basic algebra, which is nothing more than foiling this out and multiplying by I. So we come in here and we go, let's go ahead and do the algebra 2 skill. If I FOIL this out and multiply by I, and I'll leave it to you to verify, you'd get I cubed minus 2I squared plus I. I like to put parentheses to make sure that I'm including everything there. And then once I get to here, now I have a sigma with sums and differences, so I distribute the sigma through. I equals 1 to 15, and it's more tedious just writing it. And while I'm doing it, I actually always pull constants out in this step because we know how it's going to work. So instead of writing it twice, I'm just going to go ahead and pull everything out. And then the sigma I equals 1 to 15 of I. So I kind of distribute through, and then I'm going to start working my formulas. Now I'm not going to write all the formulas down, but I will remind myself that n in this problem is 15. And so when I go to use my formula, I look at my formula for the sum of I cubed, and the sum of I cubed is going to be the n squared times my n plus 1 squared all over 4 minus the constant 2. My sum of I squared is going to be that 15 n plus 1 and our 2n plus 1 all over 6 plus the sum for I is n plus 1 all over 2. And then I type it in my calculator and I get my answer of that, and you can verify that by using the summation in your calculator. So, and we're like, okay, that's great. If I'm using a calculator, why wouldn't I just use a calculator and do it? Because it's not about getting an answer. What we're really working on is the process of being able to use the formulas. And again, like I said, I'm working up to something that would be more like what you're going to see in calculus. So let's keep on going until we get to our end result. So let's look at example 4. Right? So now this is really review from the limit section. I want to calculate the limit as n goes to infinity of a sum s of n. Okay? So suppose that we've done some work, and what we've done on this is that we've already calculated a sum using those closed form formulas is 64 over n cubed n plus 1 2n plus 1 over 6. So I've managed to have a sigma that I have already eliminated the sigmas out of using the closed formulas, and I've created a formula for the sum that no longer has sigma in it. So that gets me to there. So I want to actually take the limit as n goes to infinity of this sum formula that you will have created. Now this is reminding you of prior knowledge from way back in chapter 2. It's actually limits at infinity, which is in section 4.5, I believe, in your textbook. But we have basically a rational function, and I'm going to go ahead and kind of pull in the 64 as I'm writing it. So it's 64n, n plus 1, 2n plus 1 over 6n cubed. Now, what I want you to remember is that when we're calculating limits of rational functions, the only thing that matters was the dominant term in the top and the dominant term in the bottom. Now, I obviously do not want to multiply this completely out because that would be tedious and take forever. You should be able to recognize that if you take the highest degree term part of each factor, that if I were to multiply those out, that would give me the dominant term. So I'm basically going to take 64 times n times 2n, and I get 128n cubed. Now, technically there would be plus blah, 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 blah out there, but because I'm doing the limit at infinity, I don't care about the blah, blah stuff. I only care about the dominant term. And then on the bottom, we have the 6n cubed. Then we can basically calculate our limit because we can now remove what was causing us to have infinity over infinity, the indeterminate form, and then I can take my 128 and divide by 6 and simply get 64 thirds. The limit of a constant is the constant. Okay, the limit of a constant is the constant. Now this is also something I might, while I'm here thinking about this, remind you to be very careful. On the properties that we had for summations and derivatives and limits, they were very similar. The limit of a constant times a function, pull the constant out. The derivative of a constant times a function, pull the constant out. The limit of a constant times a function, pull the constant out. The summation of a constant times a function, pull the constant out. So that all works the same. Now be very careful when we get into just a constant, not a constant times a function, because the limit of a constant is the constant, as you saw here. The derivative of a constant is 0, and the sum of a constant is the constant times n. So those have three very different rules, so you got to make sure you don't get confused as you're working with them. Okay, so I'm just going to remind you to be careful of properties. Again, the reason why I am saying this is because we may be doing a problem that has both a sigma in it, a limit in it, and we could possibly even throw a derivative if we want to, but you want to be worried and be careful of those properties and not get them confused. All right, so again, working toward where we're headed. Now what I want to do is take a look at this example 5. Notice that in this one, before I did the limit, I said you must have gotten rid of the sigma notation to get this formula. So let's practice one where we're going to get rid of the sigma notation. So rewrite the sum without sigma notation. In other words, you're going to use the closed formulas. All right, so you might be given something like the sum I equals 1 to n. Notice I'm not picking an n now. All right, it's not going to be given to you, but we'll know that we have an n in that location. That's our constant. 4i plus 1 over n squared. So I want to rewrite this without the sigma. So the very first thing that I want to stress is that this is your variable. The variable in the sigma of sigma is I. That means that everything else is a constant. N is a constant. So n squared is a constant. So when I am looking at this problem, this n squared, I'm going to pull it out of the sum because it is not the variable in the sigma. It is a constant. So I equals 1 to n of 4i plus 1. So I pull the constant out, and then I recognize that I have a sum and I can distribute the sigma through. I'm going to be very careful with my constant though, because I'm going to put parentheses, because when I distribute the sigma through, I got to make sure the 1 over n squared also distributes. And I just don't want to write it twice. So I equals 1 to n. I'm going to pull the 4 out and make that an I, plus my sum I equals 1 to n of 1. So that gets me to there. Then what you are going to do is you are going to use your closed formulas. Now, the difference between this and the problem we did previously is that we don't know n. So I'm not going to actually get a number here. I'm going to get a formula. So I use my formula for the sum of I. The sum of I is going to be n plus 1 over 2. And then I have the sum of a constant, which would be the constant times n. So I plug those in. And now the rest of it, now I'm essentially done. I've performed the task of rewriting the sum without sigma notation. But now I'm going to simplify, because that's going to make it easier to work with. And thinking ahead to what I did above, usually you're going to want to take the limit as n goes to infinity, which means I need to get it in that rational function of common denominator idea. So I'm going to go ahead and kind of distribute this n squared through. So we're going to end up, and we can cancel some things if we want to kind of make it easier. Like we'll see that the 4, this 2 will go away, and that will leave me with a 2 here. I can cancel the n squared and leave an n and that. Okay, just kind of show you a little bit of simplifying work here. And so what we would end up with is we would have 2 times n plus 1 over n plus n. I'm going to change that to be 2n plus 1 plus n squared all over n, just getting it to a common denominator. And then this would be enough for me to then work the problem and kind of go through what we're going to be working on, playing around with this. All right, so I'm going to leave that there, and what I'm going to do now is basically I just realized I had a mistake when I multiplied that through. I forgot to distribute 1 over n times n. So technically, let me fix that real quick, you would get a 1 here, and then so you would basically, getting a common denominator, only have an n there. Okay, so all of a sudden I was looking at that going, oh, I made a mistake. So I fixed that for you. All right, so now our last example in this set of notes, we're going to put it all together. What we're going to do is I'm going to ask you to calculate, I'm on number 6. So example 6. What I want you to do is I want you to calculate the limit as n goes to infinity of a sum by first removing the sigma. All right, so what we would see in the problems that we're going to be looking at is I would have the limit as n goes to infinity of some sum I equals 1 to n of 1 over n cubed I minus 1 squared, for example. So this is more like what we're going to see, and your job is going to be to calculate this limit. So your first task is to ignore the limit part of it, and it's going to be to work with the summation, and you need to remove the summation using the formulas. So bring your limit with you, good math communication. We're going to pull the constant out, 1 over n cubed. Now be careful. The constant is a constant because it's not the variable in the sum. It is not a constant for the limit, so I don't pull it out of the limit. I only pull it out of the sum. Right? And then this I minus 1 squared, because that's multiplication, I'm going to go ahead and FOIL that out. So I would get my I squared minus 2I plus 1. So I turn my product into a sum. Then we come down, and it's a lot of tedious rewriting. I'm going to now distribute my sigma through. So I have the sum. Again, when I distribute, I'm going to put parentheses. I equals 1 to n of I squared minus 2 times the sigma I equals 1 to n of I plus the sigma I equals 1 to n of 1. So I get to there. And then we're going to use our closed formulas. And again, I'm still bringing this limit down with me, bringing my 1 over n cubed. The sum of I squared is going to be, don't forget your parentheses, n plus 1, 2n plus 1 over 6, minus 2, n plus 1 all over 2, plus my constant times n. So I get myself to there. We've removed the sigma. Now we have algebra. Unfortunately, kind of algebra always kills us in calculus. My job is to get all of these together into one fraction. So I'm going to concentrate in here. Okay, and the idea is that what's your common denominator going to be? Your common denominator on this inside is going to be 6. So I'm going to have to multiply that by 3 over 3, and this I'm going to have to multiply by 6 over 6. So that's kind of what I'm doing in my head. All right? Now remember that when we're doing this, we really only want the dominant terms. And so when I'm doing it, I'm looking at it in terms of when I add all of these together, what is that going to look like? Okay. Now, one thing that we can do, and I would suggest this, is to recognize that we kind of have a common factor, and pulling that out might make this a little easier. So I'm actually going to pull that n out and put it over the n cubed so that I can look at what I have left here and say, well, what do I have? Now I can expand all of them out, or I can recognize that if I was going to multiply this out and add them together, I'm looking for the dominant term is what I'm looking for, the biggest term. That's the only thing that matters. So I'm going to have an n times a 2n here. That would give me 2n squared. Maybe we'll write it right above. All right, so 2n squared would be the dominant here. When I look at this one, I'm just going to have an n times 2 times 3, which is going to be a minus 6n on that one. Not going to be bigger than that one when we add it together. And then this is simply going to be plus a 6n over here. And it doesn't matter that there's other stuff. The dominant term, if I were to take this minus twice this plus this, the dominant term is going to be the 2n squared. So I'm going to bring only the 2n squared down and the 6 from there. So it's the magic of limits at infinity. We don't care about the blah stuff that's being added to the dominant term. So now I'm basically taking the limit as n goes to infinity of 2n cubed over 6n cubed, which you can remove your infinity over infinity problem, and then you end up with a limit of 1/3. And so that is going to be the skill that we are doing in this section 5.2. All right, so we're going to stop our review section there and post this video for anybody that needs extra help with summations.